Okay, so the third example we are going to be using is from business. All right, let's say the owners of a car rental company, all right, have determined that if they charge, well, what's happening is, if they charge customers lots of money, very high price rate to rent a car, people wouldn't rent because, let's say, hey, yeah, here's a car for rent. I'm going to charge you $1,000 per day, and nobody's going to rent that car, right? But if it's too cheap, then too many people want it, and then because the unit price or the unit rate is so cheap that you are not going to make a lot of money. So let's just assume, for the sake of this example, which by the way is very simplified because otherwise the calculations could get quite messy. But anyway, so for the purposes of this example, let's just say that the owners determined that if they charge customers P dollars per day to rent a car, that's important, where P is between 50 and 200 inclusive. Okay, so that's clearly the domain of this function, whatever the function is. The number of cars, that's N, the number of cars they rent per day, that's the demand, will be modeled by this linear function. Okay, sometimes the function is given to you because it's not as obvious as a volume function or an area function. How much should they charge to maximize the revenue? The revenue, what is the revenue? It's different from the profit, right? The profit is revenue minus the expense incurred. So the revenue is simply the sales. How much can you collect from the rent of the cars? So the revenue is the price, basically the price of renting a car per day times the number of customers. That's important for us to remember, okay? Because what this is giving you is it's not the revenue, it's the number of cars that will be rented at the price P. And this is a linear function, by the way. We can just think about this for a moment. And the y-intercept is 1,000 and goes down by 100. 5 per dollar per day, right? So it starts with 1,000. What are we talking about? This is the number of cars that will be rented at price P. And so this is what was typically known as the demand curve. Okay, this is a very simple demand curve. And what this is saying is if the price is 0, which it isn't because it's not in the domain, see that? But if the price is 0, then 1,000 people would rent a car. If the price turns out to be 200, remember 200 will make this 0. And so that's this point, that's the x-intercept or the p-intercept. If the price is 200, nobody is going to want to rent this car. And so it is going to be, or one of the cars, so it's going to be 0. And of course, you could charge $200 per day per car, but if you do that, nobody's going to rent it, so the revenue will be 0, right? And so that's how it works. And by the way, if the price is 0, 1,000 cars can be rented at the price of 0, the revenue, of course, will still be 0, right? And so this is, again, called the demand curve. All right, let's look at the revenue. This is going to be called R of P because the revenue depends on the price. Right? The revenue is the price, which is P, times the number of customers that will be renting the car at that price, which is explicitly given as 1,000 minus 5P. All right, and we are given P is between 50 and 200. I'm sure it's not going to be 200 because then the demand will be 0. Okay, so you can rewrite this in the more traditional order, negative 5p squared plus 1,000p. So it turns out to be a second degree function, otherwise known as a quadratic function. The leading coefficient is negative, so it's going to be an upside down parabola. In fact, you also know that R of 0 is 0 and R of 200, because this part will be 0, that's going to be 0, okay? So you know this point and this point already of the parabola. Now, if you know anything about parabolas, you know that the axis of symmetry and the vertex happens halfway between 0 and 200. So the answer will be 100. Okay, you can just tell by what you know about parabolas. But anyway, so let's take the derivative of this. That's negative 10 p plus 1,000. Set this equal to 0. 10p is going to be 1,000, and as I expected, p is going to be 100. Okay, so this is that point here. How do you know it's a maximum? Because it's an upside down parabola. We know this from our knowledge of what the what quadratic functions are like, and we know that the leading coefficient is negative and so on. So you know that R has its maximum. And by the way, this is the only leading, this is the only critical point, right? So R has its maximum at P is equal to $100. Now, if you insist on, using our rules for finding the absolute maximum and absolute minimum, what you can do is you find the value of the function at the critical points. And in fact, there's only one critical point. So if you plug in 100 here for this equation, you have $100 that you collect from, let's say, looks like 500 people. So that's going to be $50,000. That's the maximum revenue that you can obtain using this model. All right. There's one more thing I wanted to say. Oh yeah, so if you insist on finding, absolute maximum, absolute minimum, and so on, you have the critical point, only one. So you calculate the value at the function, which happens to be 50,000. And you calculate the value at the endpoints, but R of 0 is 0, R of 200 is 0. So these are the minimum, absolute minimum, and this is the absolute maximum. And so the answer is that R has its maximum if the price is $100 per day, and at which rate the daily revenue will be $50,000. Okay, great. One last question. All right, this time we want to minimize something. Let's find a problem. Here is a problem, minimizing the surface area. And this is sort of an important kind of a problem for engineering. If you are in, let's say, manufacturing engineering or something, right? And let's say you have a can, it's a cylinder. Of course, many cans are cylindrical, right? As such, you have the radius that you can control, and then you have height, right? So H and R are something that you can decide. Now, the reason you want to minimize the surface area is maybe because this metal costs a lot of money, and if you want to contain the same volume, a given volume, you want to minimize the surface area, right? So let's say we want the volume to be 20 cubic inches. By the way, I looked it up. Okay, this is approximately 328 cubic centimeters or milliliters, and that's about the size of a typical can, like the can of soft drink that you can get. So 20 cubic inches is just like your soda can, right? So that's the volume that you want, but you want to minimize the surface area. As a manufacturing engineer, you want to tell your company, hey, you don't want to make this way too long like this, or way too thick or big like this, because then you would end up using a lot more surface, which will cost your company a lot of money, right? So you want to minimize the surface area, okay? And given the constraint that the volume is going to be 20 cubic inches. All right, so that's all I already wrote, minimize the surface area. And let's just say given that the volume has to be 20 cubic inches. So that's all the problem says. Now, can you do this problem? What do you know about the volume and the area? Okay, well, the area, if you open this up, it's going to look like this. That a side, the round side, can be opened up like this. And so the height is still here. Now, what's the length of this? Well, that's going to be the circumference, right? Because this thing here turns out to be the same line here. And so the circumference of the circle of radius r is 2 pi r. How do you know that? Well, I hope you do know this. Okay, this is something you should have learned years ago. But again, if you don't know that, you may want to review these basic formulas from geometry. And if it's too complicated, or if it's a formula that I cannot expect most students to remember, then I will give you these formulas. All right. But you again should be familiar with the circumference and the area of a circle and so on. All right, now you do have the top, the circle, and the bottom circle, right? And so you do have to include those because that's a part of the surface area. All right, we know the volume, or do you know the volume of a circular cylinder? It is the base area, which is pi r square times the height. Okay, that's the volume formula. And you want this to be 20. Now, this is the constraint because you're given this as a requirement. And under this constraint, or subject to this constraint that pi r square h is 20, now you want to maximize this, sorry, not maximize, minimize the surface area, which is, okay, so this is pi r square. You have two of these because you have one on the top and one on the bottom, plus the rectangular region, which is 2 pi r h. This is what you are to minimize. Notice here, I have r and h, two independent variables, which you should not have. So, I mean, one of them you should have. So how do you replace one with the other? And of course, the answer, just like in our first example, is found in the constraint. Okay, so let's say this constraint gives us, which one do you want to solve for? Maybe it's easier to solve for h, right? Because r is squared. So let's say h is 20 over pi r square. That seems to be right, right? So now a can be written as a function of one variable, I hope, 2 pi r square plus 2 pi r times h, which is now replaced with 20 over pi r square. All right, and easily you can cancel the pi, and one of these r's can be canceled. Okay, let's rewrite the function to be minimized. A is 2 pi r square plus, it looks like 2 times 20, 40 divided by r. Okay, remember, you still have that one r left on the bottom. Also, you can write this as 2 pi r square plus 40 r to the minus 1 if you like. But notice here, now this is a function of one variable, namely r. Okay, so we can take the derivative. Now, by the way, we should go back and make sure we understand what r can be. What can r be? Now, r is the radius, so it can't possibly be 0. It can't be negative. Well, I mean, I just put 0 is less than or equal to, because if, well, here you can't really, you cannot let r be 0, because what happens if r is 0? You can't possibly get the volume of 20. Okay, so r can be very, very, very small. R can be 0.0001. But in that case, in order to obtain the volume of 20 cubic inches, your can is going to be like this, right? All right, and that's of course very unreasonable. The surface area seems to go to infinity because as r shrinks down to 0, h is going to go up to infinity. So okay, that's probably not good. You'll have a very hard time holding the can or drinking from the can, which is like miles tall. All right, so what's the biggest size of r? Okay, now again, r could be like thousands. That's going to, because the volume is fixed, that's going to make h really, really small. Okay, so that's going to be hardly close the can. Its surface area is going to again go to infinity because r is getting bigger and bigger, and so this is no longer a can. It's almost like a flat piece of metal, although it's not. Okay, so so there, I can't really tell you what the there is no closed and bounded interval for the domain of this function. Okay, so we'll just have to decide what to do with this. Okay, and in this in the book, these problems are specified as the problems where solving optimization problems when the interval is not closed or is unbounded. So you have a not closed and unbounded domain for this function. That's okay. Usually it's not a problem, okay, because of, well, you watch what happens with this. Take the derivative of this. It's 4 pi r and then negative 40 times r to the negative 2, or you can write this as minus 40 over r squared. Set this equal to 0. Maybe it's easier if you write it this way, 40 r squared. Now remember, r is not 0, okay? So you can multiply both sides by r squared. And by the way, in order to write even something like this, you know that r can't be equal to 0. So what I said is probably not that relevant. Multiply both sides by r squared, and you get this. Pi r cubed is 10. So r cubed is 10 over pi. And so r is the cube root of 10 over pi. All right, at this point, you take your calculator and you write down your answer. And that's going to be about 1.471. 1.471 watt, okay? Our volume was described or expressed in terms of cubic inches. So this, the unit we are needing for R is inches, okay? So that is what we have, okay? But you don't know if this is where A is maximum or minimum or whatever, right? So let's do a little analysis and figure out what we can tell. Because there is, in this case, there is no endpoint, right? What is going on here? Well, it is first of all rational function, so you're going to have some asymptote. R is here, and A of R is on the vertical axis, and it looks like we are trying to, of course, draw the that equation or graph of that function, and you realize the limit of A of R as R approaches 0 from the positive side. Remember, R is not negative, so you only approach 0 from the positive side. But as you do so, this part becomes 0, but this part blows up. I mean, R goes to 0 from the positive side, so 40 divided by R goes to infinity. Okay, so you have a vertical asymptote right here. What else is true? Well, now you know 2 pi r. See, so as r approaches infinity, by the way, you realize we have been using all of these techniques we learned, right? Right now we are looking at limited infinity, which is in 4.6, the previous section. We also talked about the shapes of the graph, which is in 4.5. And so, and then 4.3 had to do with maxima and minima. So we are using lots of these things that we have learned prior to this section in chapter 4, which is, again, the nature of mathematics. We build on what has been learned already, which is why it's so important to learn and master every section before you go to the next section, with a few exceptions. Okay, so as R approaches infinity, this goes to 0. And so this becomes closer to 2 pi r squared. Now, this is not a good way to write this. Maybe I shouldn't have written this as an, yeah, here, let me go ahead and not this, because I hate to write limit is equal to and then another function here. So what I should say is, as R approaches infinity, A of R, okay, remember the last term becomes closer and closer to 0. This becomes closer and closer to 2 pi r squared. Now, 2 pi r squared is a parabola with a coefficient 2 pi, which is like 6.28 something. Okay? So the graph of A gets closer and closer to 2 pi r squared. Now, unfortunately, because it's, well, I don't know if it's fortunate or unfortunate, but it is a parabola. It's not a straight line. So this is not going to give you any sort of an asymptote which has to be a line by definition. So what happens is though, this is going to be slightly bigger than 0 as r approaches infinity. So the graph will get the graph of A is going to be slightly above this, but gets closer and closer to the parabola. And we have this, which means it has to approaches infinity as x approaches 0 from the right. And so the graph is going to necessarily look like this. Okay, there has to be a minimum point, and we have identified this minimum point to be where r is about 1.47 inches. Okay, so from the shape of the graph and from what we know about asymptotes and the limits, we know that this must be a minimum point. Okay. Now, if you can, of course, you can do a second derivative, and the second derivative test is going to give you something too. Where is my first derivative? This is my first derivative. The second derivative is going to be 4 pi plus 80 over R3. If I remember, I mean, if I do this right, negative 40 times negative 2 is positive 80. And then the new exponent will be negative 3. So that, all right. And if you plug in 1.47 here, this is already like over 12 something plus 80 over a number. Whatever this is going to be positive. Okay. So that means A has a local minimum, just like we predicted. We knew that the shape of the graph has to be this. So we knew that A must have a local minimum at 1.47, this point that we found to be a critical point. And of course, again, well, let's see. When when R is positive, this will be an absolute minimum. Okay. It turns out if you do the other side, you remember if R were allowed to be negative, okay, it's going to have a negative. The function goes to negative infinity as R approaches 0 from the opposite side, as from the left-hand side, just because this thing was not that. This term becomes closer and closer to negative infinity, as R approaches 0 from the negative side. But then as R approaches negative infinity, this thing becomes 0, and the problem or the function gets closer and closer to the parabola. So it'll start to go like this. So the entire function, the whole function A of R, if it's defined over all reals except 0, the graph is going to look like this thing here. Okay, but again, we are only focused on R being positive. So you could say in that domain, A has a local minimum and an absolute minimum at 1.471. And by the way, we never calculated this thing here. Okay, so this is, what is that? 2 pi times this square plus 40 divided by that. Okay, it's approximately going to be 40.788 square inches. And so this is the minimum surface area required in order to come up with a cylindrical circular cylinder can whose volume is 20 cubic inches. Okay, and if somebody says, no, I can save more money by making this area smaller, you say, no, you are lying, and I can prove it. And here's your proof. Okay, you have found the absolute minimum value for A, and you have found the radius that would attain that, which is this. Okay, great. So this is what optimization problems look like. Now it's your turn to solve a wide variety of problems.